The sun, a luminous sphere of plasma, dominates our sky with unwavering brilliance. From Earth, it seems constant, dependable, a life-giving orb whose presence is so familiar that we often forget its extraordinary power. Yet when we peer into the depths of space, the sun transforms from a common star into a singular phenomenon, a medium-sized G-type main sequence star among billions in our galaxy, and simultaneously a cosmic yardstick against which all other stars are measured. Its light reaches us across 149.6 million kilometers, warming the atmosphere, driving weather, sustaining photosynthesis, and shaping the very conditions that make life possible. But the sun is also a living nuclear furnace, a star in constant flux, its energy output, magnetic fields, and atmospheric activity revealing the intricate mechanisms of stellar physics. Observing it inspires not only awe, but profound scientific inquiry. How does it function? How does it compare to the universe's most enormous stars? Can it help us understand the ultimate limits of stellar scale and energy? At its core, the sun is powered by nuclear fusion, a process that converts hydrogen into helium, releasing energy according to Einstein's equation, E equals mc2. This reaction occurs under pressures exceeding 250 billion atmospheres and temperatures reaching 15 million degrees Celsius. The fusion process generates photons, neutrinos, and a continuous outward flow of energy that eventually emerges as sunlight. Over 99.8% of the solar system's mass resides in the sun. Every second it converts approximately 600 million tons of hydrogen into helium, emitting 3.8 times 1026 watts of energy. This immense energy output defines not only our planet's climate and ecosystems, but also the behavior of the heliosphere, the vast bubble of charged particles and magnetic influence that extends beyond Pluto and shields the solar system from cosmic rays. The sun's layers reveal the complexities of stellar structure. Surrounding the core is the radiative zone, where photons are absorbed and re-emitted countless times, taking hundreds of thousands of years to reach the outer layers. Beyond that lies the convective zone, where turbulent plasma motion transports energy more efficiently toward the surface. The visible surface, the photosphere, radiates the sunlight that bathes Earth, averaging a temperature of about 5 The chromosphere and corona form the solar atmosphere. The corona, extending millions of kilometers into space, reaches temperatures of 1 to 3 million degrees Celsius, far hotter than the surface itself. This paradox remains an area of active research, with magnetic reconnection and wave heating as leading explanations. Solar winds, composed of charged particles from the corona, continuously stream through the solar system, influencing planetary magnetospheres and contributing to auroras. When comparing the sun to the largest stars known in the universe, its relative size is modest. Stars such as Scuti, Canis, Majoris, and Stephenson 218 dwarf our sun in radius and luminosity. The sun's radius is approximately 696,000 kilometers, whereas the largest known stars exceed 1,700 times this size, stretching beyond the orbit of Jupiter in some cases. Yet the sun's importance is not measured solely in size, but in its relationship with life, its stability, and its role as a stellar laboratory. Unlike massive supergiants, which live fast and die in catastrophic supernova, the sun's moderate mass grants it a lifespan of about 10 billion years, allowing billions of years of stable conditions for life to emerge and evolve on surrounding planets. This longevity is a profound factor in Earth's habitability and highlights the significance of stellar scale not merely in physical dimensions but in temporal and energetic stability. The sun is also a magnetic powerhouse. Its magnetic field drives sunspots, solar flares, and coronal mass ejections. Sunspots, cooler regions on the photosphere caused by concentrated magnetic flux, follow an 11-year cycle of activity, influencing solar irradiance and space weather. Solar flares release enormous bursts of electromagnetic radiation, while coronal mass ejections expel plasma that can disrupt satellite communications, power grids, and even auroral activity on Earth. The study of these phenomena, heliophysics, informs our understanding of stellar magnetic behavior, particle acceleration, and the interactions between stars and their planetary systems. Observations from spacecraft such as the Solar Dynamics Observatory, Parker Solar Probe, and Solar and Heliospheric Observatory provide unprecedented insight into the sun's magnetic complexity. In exploring the largest stars, we confront extreme conditions that test the limits of stellar physics. Supergiants like Canis Majoris are so vast and luminous that they challenge models of energy transport and stability. Their lifespans are measured in millions of years, short compared to the sun, and their outer layers are tenuous, susceptible to massive eruptions and shedding of stellar material. These stars illustrate the principles of hydrostatic equilibrium, radiation pressure, and gravitational binding in extreme contexts. They also emphasize the rarity and fragility of life-sustaining stars like the Sun. While the Sun is neither the largest nor the most luminous, it exemplifies a balance that allows planetary systems to persist long enough for life to develop. The Sun's energy reaches Earth after traversing the vacuum of space in approximately 8 minutes. This journey represents both the speed of light and the immediacy of solar influence on climate, weather, and biological cycles. Variations in solar activity, including the solar cycle, affect Earth's upper atmosphere, climate patterns, and cosmic ray flux. Observing and understanding these variations is crucial for predicting space weather and protecting technological infrastructure. Sunlight also drives photosynthesis, forming the foundation of the biosphere's energy pyramid, from plankton in the oceans to forests and human agriculture. In this way, the Sun's steady output integrates physics, chemistry, and biology into an interconnected system sustaining life on our planet. Solar observations also reveal the dynamic nature of plasma and fluid interactions. Granules on the photosphere, roughly 1,000 kilometers across, represent convective cells transporting energy from the Sun's interior. Supergranules, magnetic flux tubes, and prominences highlight the interplay of heat, motion, and magnetism. Eruptive phenomena illustrate nonlinear dynamics, instabilities, and the conversion of magnetic energy into kinetic and thermal energy. Understanding these processes informs astrophysics across scales, from protostars to supermassive stars, and even phenomena in galaxies. The Sun becomes a microcosm for universal processes, offering a nearby laboratory to observe fundamental physical principles. Comparing the Sun to massive stars in the universe emphasizes the extraordinary diversity of stellar evolution. Hypergiants and red supergiants exist on the upper extremes of mass and luminosity. They are fueled by intense fusion reactions, rapidly consuming hydrogen and progressing through heavier elements. Their immense energy output drives violent winds, mass loss, and eventual supernova explosions. These events seed the interstellar medium with heavy elements, enabling the formation of new stars and planets. In this context, the Sun is moderate but essential. It sustains life without immediate destruction and provides a stable platform from which intelligent life can evolve and observe the cosmos. From a motivational perspective, the Sun's existence embodies the balance of power and consistency. It is neither the largest nor the most extreme, yet it defines the conditions for life. Its measured energy output, predictable cycles, and relatively stable magnetic behavior allow ecosystems to flourish and civilizations to arise. In contemplating stars larger than the Sun, humans gain perspective. Extreme size or power does not necessarily equate to sustainability or life potential. The Sun teaches that moderation, stability, and enduring presence are as remarkable as sheer magnitude. Stellar classification places the Sun in context. It is a G2V star, a main sequence dwarf with moderate mass and temperature. This classification reveals insights into fusion rates, spectral output, and surface temperature. The Sun's yellowish-white light provides the ideal spectrum for photosynthesis, emphasizing the relationship between stellar physics and biological suitability. Main sequence stars like the Sun dominate the Milky Way's stellar population, serving as anchors for planetary systems that might host life. Their longevity contrasts with the ephemeral brilliance of supergiants, emphasizing that the greatest impact often comes from sustained, steady influence rather than temporary extremes. In the vastness of the universe, where stars millions of times more massive and luminous than the Sun exist, our star's significance is defined not by scale alone, but by its function, stability, and relationship to planetary life. The Sun exemplifies how stars operate as engines of energy, chemistry, and structure. Its nuclear core, convective layers, magnetic dynamics, and atmospheric phenomena illustrate fundamental physics while directly affecting life on Earth. Observing other stars expands our understanding of extremes, but the Sun remains uniquely relevant to human existence, a nearby laboratory and a cosmic motivator. As we explore the largest stars, the Sun serves as a baseline, a point of comparison that illuminates the extremes of stellar evolution. While UI Scuti and Stephenson 218 dwarf the Sun in size, their instability, short lifespans, and violent outbursts highlight the precarious nature of extreme stellar power. The Sun's energy, moderate size, and stability demonstrate that significance is not solely measured by physical magnitude. It underscores the interplay between physics and life potential, between energy output and longevity, between cosmic scale and human perspective. The Sun, in documentary observation, becomes both a teacher and a lens. It teaches the principles of nuclear fusion, energy transport, plasma dynamics, and magnetism. It provides perspective on the range of possibilities in stellar evolution. It inspires reflection on stability, sustainability, and the conditions necessary for life. Its brilliance is both literal and metaphorical. Light as energy, light as inspiration. In this way, studying the sun bridges science and human aspiration, revealing how understanding our local star illuminates both the universe and our place within it. Across billions of years, the sun has sustained life, driven planetary systems, and enabled civilizations to ponder the cosmos. It continues to provide energy, insight, and inspiration. While it is not the largest star in the universe, its role is unparalleled in relevance and impact. The sun is a testament to the principle that power is meaningful not in scale alone, but in stability, continuity, and the capacity to nurture complexity. Its presence motivates scientific inquiry, encourages awe, and inspires generations to explore the boundaries of both space and knowledge. In contemplating whether the sun is the largest star, the answer lies not in physical dimensions but in context and consequence. The sun's size, energy, and lifespan are perfectly tuned for the emergence of life on Earth. Its solar cycles, magnetic activity, and plasma dynamics offer endless scientific intrigue. Its light reaches every corner of the planet, supporting ecosystems, weather, and human endeavor. In comparing it to colossal stars, we gain perspective on extremes, yet also appreciation for extraordinary balance and function of our own sun. It is a reminder that greatness can reside in stability, reliability, and the ability to sustain life over cosmic time, offering lessons that are both scientific and profoundly motivational. The sun, modest in cosmic terms yet immense in significance, stands as a symbol of energy, persistence, and inspiration. It illuminates Earth and human understanding alike. By studying it and comparing it to the universe's largest stars, we gain insight into the mechanics of the cosmos, the principles of stellar physics, and the conditions that make life possible. The sun is a living laboratory, a cosmic mentor, and a source of enduring wonder, a star whose relevance transcends size, whose lessons endure across space and time, and whose light continues to inspire both scientific discovery and human aspiration.